Hello, this will be a demonstration of Proposition 2 from Book 6 of Euclid's Elements, which says that if a straight line be drawn parallel to one of the sides of a triangle, it will cut the remaining sides of the triangle proportionately, and conversely, if two of the sides of the triangle be cut proportionately, the straight line connected by the points of section is parallel to the remaining side. So this is one of those propositions that contains its own converse, so accordingly we're going to have two different givens. What's going to be common is the triangle ABC, like so. And in our first case, we're going to have the straight line DE be parallel to BC, like so. And what we're going to prove is that the remaining two sides, so the sides to which DE is not proportional, that these sides are cut proportionately. Namely, that BD is to DA, just as CE is to EA. So that's the first given, that's the first thing we're going to prove. Accordingly, what we're going to do is we're going to join the straight lines of BE and DC. We're going to do that obviously by postulate 1. Now, because the two triangles BDE and CDE are on the same base and they're in the same parallels, right? We were given that DE is parallel to a BC. So they're on the same base and in the same parallels, which means by proposition 137, they are equal to each other. Triangles on the same base and in the same parallels or under the same height are equal to each other, and so the triangle BDE is equal to the triangle CDE. And we know by proposition 5.7 that equal magnitudes have the same ratio to the same magnitude, which means we can say that the triangle BDE is to the triangle ADE, just as the triangle CDE is to the triangle ADE. But we know that the triangle BDE is to the triangle ADE, just as BD is to DA. We know this by proposition 6.1. These two triangles, BDE and ADE, are under the same height. They are in the same parallels, which means they are to each other as their bases. So that the triangle BDE is to the triangle ADE, just as the base BD is to the base DA. Now, similarly, we know that the triangle CDE is to the triangle ADE, just as the base CE is to the base EA, again by 6.1, which means that we have ratios which are the same with the same ratio, which means they are the same with one another. That's proposition 5.11, which means that we can substitute these ratios in triangle BDE to triangle ADE and triangle CDE to triangle ADE for base BD to DA to base BD to base DA and base CE to EA respectively, which means that we can say that the base or the straight line BD is to the straight line DA, just as the straight line CE is to the straight line CA. Again, that's by proposition 5.11. And this is what we set out to prove. Given that DE is parallel to BC, we wanted to prove that BD is to that the straight line BD is to the straight line DA, just as the straight line CE is to the straight line EA, and we have just proven that, which means we are done with the first part of this proposition. Now the second part, proving the converse, we're going to be given that there are 2 points on BA and CA such that BD is to DA, just as CE is to EA. And what we're going to prove is that DE, which joins the points of section, is parallel to the remaining side, namely BC. Again, we're going to join the straight lines BE and DC by postulate 1. Now, we know that the triangle BDE is to the triangle ADE, just as the straight line BD is to the straight line DA. Again, by proposition 6.1, these two triangles BDE and ADE are under the same height. They are in the same parallels, which means they are to each other as their bases. And likewise, by 6.1, we know that the triangle CDE is to the triangle ADE, just as the base CE is to the base EA, which means again by two uses of proposition 5.11, the common notion 1 of ratios, we can say that, that the triangle BDE is to the triangle ADE, just as the triangle CDE is also to the triangle ADE. Now, we have two magnitudes which have the same ratio to the same magnitude, which means that proposition 5, 9, they are equal to each other. And so the triangle BDE being to the triangle ADE, just as the triangle CDE is to the triangle ADE, we can therefore conclude that the triangle BDE is equal to the triangle CDE, again because those two triangles have to the same triangle the same ratio, which means by 5, 9 they're equal to each other. And these two triangles, BDE and CDE, are equal to each other, and they are evidently on the same base, namely DE, which means by proposition 139, they must be equal to each other. We have equal triangles on the same base, which means they are in the same parallels, so that we can say that DE is parallel to BC. And this is what we set out to prove. Given that BD is to DA, just as CE is to EA, we wanted to prove that DE is parallel to BC, and we've just done that, which means we are done with the second part of the proposition, we are done with the final part of the proposition, which means we are done with the entire proposition, therefore, etc., QED. So another very useful proposition, this and 6.1 come up loads of times in book 6 and beyond, so very important props to remember. So this is one that you should just kind of know like that. Other than that recommendation, I have nothing to say about this proposition, so I will end the video here and move on to 6.3.